Okay, so for our last talk today, Matthias Hutzler would like to speak about the big infinitesimal-topos as a classifier.
Thank you. I'd like to thank all of the organizers first for bringing us together at this conference, and in particular, I'm thankful for the opportunity to give a talk here. It's actually, for me, the first talk of this kind, so I'm very excited. I'm aware that it's the 12th talk for you to listen to today, so in case you're feeling a little bit tired or exhausted, you're really not to blame for it. I've tried to make the talk very accessible, and I'm trying to make it entertaining. And also I have a promise on you for you on the next slide, in an attempt to keep you motivated throughout the talk. But first, yes, I'm talking about the infinitesimal-topos. And actually there's a big and small version of the infinitesimal-topos, and I hate when people don't say which one they mean, so I wrote it here, the big infinitesimal-topos. And this is a topos from algebraic-geometry. There are several toposes in algebraic geometry that people use to compute some crazy topology or some crazy schemes. That's not what I want to do today. I want to understand the infinitesimal-topos from another perspective. More generally speaking, the goal is to understand toposes from algebraic geometry. From a logical perspective, we will see what this means. But I can say it in one sentence if you know what a classifying topos is, because what I want to do is I want to give a reasonable theory classified by the infinitesimal topos. Okay, and here's a promise for you. You will fully understand the key ingredient of the proof. Isn't that great? So even if you don't understand everything before, there will be a point where I say this is the key ingredient, and if you fall asleep, then that's the point to wake up again, because you will be fully able to understand it. Actually, I would say the core of the argument could be explained to undergraduate students who have managed to pass an algebra class. But of course, we will use this simple argument in a not entirely trivial way. Okay, and if you want to be honest, it's a simplified case where this argument is central. Okay, first of all, a quick reminder about toposes. Probably many of you don't need this, but anyway, the first example of a topos, and this will be our favorite example in this talk, is a pre-sheaf topos. So for any small category C, the pre-sheafs on C are a topos. And unfortunately, there are more examples. We want sheaves on a topological space to be a topos, and the general definition is kind of exactly the common generalization of these two examples. So a topos is given by a site, namely a site consists of a small category C, and a golden topology J on C, and you don't really have to know the details. All you have to know is the golden topology distinguishes some families with a common codomain as covering families, and then a pre-sheaf has to satisfy a certain gluing condition for every covering family to be called a sheaf. So more covering families means less sheaves. And then the category of sheaves on the side is a golden topos, and we want any category which is equivalent to such point to be a golden topos too. That's the definition. So, yeah, and actually the topology J selects the sheaves among all the pre-sheaves in a nice way, meaning that it's not just some arbitrary full subcategory, but we have a geometric embedding, so this is subtopos then. Okay. Next, geometric theories. Because as I said, I want to give a geometric theory that is classified by the infinitesimal-topos. And geometric theory consists of sorts, function symbols, relation symbols, and axioms. And if you haven't seen it before, I assume most have seen it before, but if you haven't, then the only way to wrap your head around this is by an example, I think. So the theory of rings consists of one sort, which we mentioned as the set where we have ring operations on. So we have 5 function symbols, which are the ring operations, including the 2 constants 0 and 1. We have no relation symbols, and we have 8 axioms. I've written out 2 of them here. 0 plus x should always be x, and the ring should be commutative, because whenever I say ring, I mean commutative ring unit. Okay, but these this example of a geometric theory is actually a bit boring because all the axioms are equations, and this is called an algebraic theory. A geometric theory is much more expressive. Namely, the axioms of a geometric theory have this form: phi entails psi. So this is called turnstile, and they speak it as entails. And you should imagine it as an implication, but we want another symbol for it. And phi psi should be geometrically formulated here. This means that they have to be built from atomic formulae only using certain logic combinators among others, namely top and bottom, the true and false formula, conjunction and disjunction, also infinitary disjunction and existential quantifier are allowed in geometric formulae, but not infinitary conjunction, universal quantification, implication, or negation. So here on the right we have now the theory of local rings to have something a little bit more interesting. What does it mean for a ring to be local? So I don't want to say something like has a unique maximal ideal or something, because that doesn't behave well intuitively. A ring is local if 0 equals 1 entails bottom. In other words, it's not a 0 ring. And whenever x plus y equals 1, then either x is invertible or y is invertible. So these are local rings, and that's an example of a geometric theory because, well, these forbidden symbols do not appear in these axioms. And also the equation axioms had to be changed a little bit, namely we just write top and tails in front of them such that they are of this form. Okay, now what do we want to do with geometric theories? We want to look at models in toposes, because you can think of toposes as categories which are good enough to interpret geometric logic within them. And this means that for a topos E and a theory T, we can form this category here, T of E, which stands for the models of T and E. There are other notations like T mod of E, but for me it's convenient to have a very short notation because why not? That's a natural thing to do. So we can look at the models of a theory T in toposes, and then we can ask if there's a classifying topos for a theory T. Classifying topos is denoted set T, and it should have this property that the models in an arbitrary topos E correspond exactly to the geometric morphisms from E into the classifying topos. So I didn't explain what geometric morphism is because again we don't need the details of that, but it's the natural notion of morphism between toposes, at least if you're interested in the geometric way. Okay, so of course to make this precise, this is an equivalence of categories, and there are there's a certain coherence condition this has to satisfy, but you can also put it in other words, namely there's a universal model of T in the classifying topos. That is, we have a T model in set T, and sorry for that, this T shouldn't be a blackboard bulge T like this. There's a universal T model in set T, in the sense that whenever I have any model of the theory in any topos E, then I can get this as a pullback of the universal model along a geometric morphism. And this is exactly this category equivalence here. Okay, and then of course the question is, do classifying toposes exist? And yes, they do. Every geometric theory has a classifying topos, and also every topos classifies some geometric theory. Now, we could say this settles in particular the question whether the infintesimal-topos is a classifying topos, because every topos is a classifying topos for some theory. So that's not the question that the title is referring to. There's definitely some geometric theory, but this theory only gives us a theory that, well, that's not very understandable, not very nice. We want to have a nice theory that's classified by the infinitesimal. Okay. Yeah, as I said, primitive toposes are our favorite toposes in this talk. So when I have a theory, I can ask whether the classifying topos can be presented as a primitive topos. And keep in mind, one topos can usually be presented by many different sites and also many different theories, at least different looking theories can have the same classifying topos, which then means that they also have the same models in any topos, and this is called Morita equivalence. But so the question is, when I have theory T, can I present set T as a three-sheaf topos with a small category C? And so if you like three-sheaf topos, then you would hope that this is true for many theories. And here are a few examples. Algebraic theories are always three-sheaf type. Also, Horn theories are three-sheaf type. A Horn theory is one that cannot only contain equational axioms, but can contain finite conjunctions of atomic formula. Okay, and also any Cartesian theories of three-sheaf type. Cartesian theory can, additionally to finite conjunctions, use existential quantifiers in its axioms, but only if these existential quantifiers can be shown to refer to unique existence. Yes, and this is okay. This is necessary so that we know automatically that theories of three-sheaf type. But as we know that two theories can look quite different but still be Hermite equivalent, so it's clear that a theory might not be a Cartesian theory as it is stated, but could be three-sheaf type anyway. So here's a theorem that tells us why, what benefit we have from theories of three-sheaf type. Because, okay, what does it say? If T is a theory of three-sheaf type, then the classifying topos for T can be presented in a canonical way, namely this here. Okay, what's that? That's definitely a three-sheaf topos again, okay. But it's particular canonical three-sheaf topos. Namely, here we have the set-based T models, and then we, of the category of set-based T models, we only take the compact objects, so the co-representative functor should serve critical coordinates. And this is a bit surprising maybe, because usually geometric theory is not at all completely determined by its set-based models. But if it is a theory of three-sheaf type, so if we have managed to present the classifying topos in some way as a three-sheaf topos, then it lets us conclude that the theory is actually determined by its set-based models, because we take the category of set-based models and then perform this categorical construction of taking the compact objects. Okay, and I learned this theorem from a book by Olivier Caramello, theory science toposes, and I felt that this was really a good guidance for my work with classifying toposes, because now I knew it whenever I have a theory and I can find out that it is of three-sheaf type, that's all I need to know about the theory. So the only thing that remains then is to determine its compact set-based models. Okay, and it also gives us nice examples. The theory of rings is an algebraic theory, so it's of three-sheaf type. So it is classified by this topos here. We take the category of rings and take the compact objects. These are exactly the finitely generated rings. So the set value functor on finitely generated rings, that's the classifier for rings. And another example is the object classifier. So there's a theory of objects which has only one sort and nothing else. And the set-based models are all sets, and the compact objects in the category of sets are the finite sets. Okay, but yeah, as I said, sometimes theories have axioms that are not Cartesian, and we wonder, well, we can describe the classifying topos anyway. The way to think about it is also sometimes we can show that the classifying topos is still a three-sheaf topos, but if it's not the case, then the way to think about this is we first leave out these axioms and say, okay, let's look at the algebraic or maybe one part of the theory, and this is, we know a classifying topos for that, and now we add additional axioms. Additional axioms means the theory has less models in all toposes, and if you think that this should exactly correspond to a subtopos of the classifying topos, then you are entirely right. So additional axioms means taking the subtopos of the classifying topos, and subtopos, when I have a site of definition for a topos, then the subtopos of the topos corresponds to a stronger Golden topology. on the side. Okay, and this correspondence between additional axioms and a stronger topology, I will not spell it out in detail, but I will give an example to give you a feeling how it works. We take the theory of rings again, and we take these additional axioms. These are exactly axioms for a local ring. And the first axiom says 0 equals 1 takes bottom. And for the topology, this means the zero ring, which is the only model that satisfies 0 equals 1, is covered by the empty family, because bottom corresponds to the empty family. And then the other axiom, if x equals y, if x plus y equals 1, then one of them is invertible. This means when I have a ring A and I have some x and y such that x plus y equals 1, then A is covered by two arrows where I universally make invertible the elements x and here y. Okay, and this gives us a topology on the category of finally generated rings, and this topology has a name. It's exactly the Zariski topology. So as a corollary, we obtain the big Zariski topos, classifies the theory of local rings.
What means big? What's the meaning of big?
So by the small Zariski topos, I would just mean sheaves on X, sheaves on a side, or sheaves on a
scheme.
On scheme.
Yes. So sheaves on X for X scheme. I would maybe call this the little Zariski topos, or small, and the big Zariski topos is then probably usual.
Okay. It's called the Zariski topos.
Okay.
Right. Yeah, we don't need to have big.
But for the infinitesimal topos, there is a big and a small version, right?
No, but here, I don't know.
Okay, you would say
I would say
so.
Zariski topos.
Okay. Okay, good. Okay, we have obtained this result, and this is actually historically the first example of a classifying topos that was described. And yeah, we can ask the question, what about other toposes from algebraic geometry? And so for a long time it is well known that the étale topos classifies separably closed local rings, and that's additional axioms for the theory of local rings, because the étale topos is a subtopos of the Zariski topos. But the infinitesimal topos is not a subtopos of the Zariski topos. So this is a bit different. And here's it, definition of the infinitesimal topos in a simplified version. The infinitesimal topos is given by a site, and the category of the site is this: finitely generated rings A with a finitely generated ideal little a, such that every element of the ideal is nilpotent. And actually the opposite of that category, because this is an algebraic category, and sites we should always think of as geometric categories. Okay, and here's a picture to visualize this. So this first line here, this is one model of the theory. We have a ring and an ideal sitting in that ring. And if we have another model, then what's a morphism? A morphism is just a ring homomorphism, but it should send the ideal little a to little a prime. Okay, and this looks very good, because this is the category of compact models for a certain geometric theory. I call it T-in for infinitesimal topos. And if you want to know what the theory is, then just read this sentence here again. And out the finitely generated. So it's the theory of a ring A together with an ideal such that element of the ideal is nilpotent.
I'm sorry,
Yes.
I don't get what is J. What is the topology?
The topology is not here. Here it is. It wasn't here before. I didn't show it. Now it is. Okay. I just wanted to say that we can understand the category as this category of compact models. And I hope that you believe me that compact model means exactly that the ring is finitely generated and that the idea is finitely generated by a few hundred channels. Okay, and the topology for the infinitesimal topos is just the Zariski topology again. It might not be entirely clear what I mean by that, but you can give similar covers of this ring A here, as in the case of the Zariski topos. And then it should be quite plausible that this topology will again correspond to an axiom saying that the ring is local. Okay, so are we done? Is that it? Have we found the theory? Is it this T-inf plus local ring axioms? Well, there's one bit missing, namely, this is the category of compact set-based models, but the category of compact set-based models is only interesting if the theory is of pre-shift type. So the key ingredient that's missing is T-inf of pre-shift type. And I've written the relevant part of the theory out here, and this is the part where you should wake up if you have been asleep, because we want to find out, can we reformulate this here in a way such that it is obviously of pre-shift type. So the first 3 lines just say that A is an ideal, not very interesting, and it's not very problematic because there are only finite conjunctions. But the 4th line says every element of A is nilpotent, and that requires an infinitary disjunction, and disjunction is not allowed for Cartesian theories. So I can't see if this theory is Cartesian. We have to reformulate the situation. So the situation is we have an ideal in a ring, and every element is nilpotent. We have to reformulate this in a way such that we can formulate it with less complex logical formulas. You have to get rid of this disjunction. Okay, and the way to do this is we stratify this locally nilpotent ideal. We don't talk about the ideal as a whole. We only talk about parts AN of the ideal. So we need countably many relation symbols, but that's not a problem at all. And this line here says, okay, if x is an AN, then it should be already 0 if taken to the power of n. And then it should also lie in the next AN plus 1, and this means also the other direction is in axiom 2, so this is necessary to make the stratification unique. And yeah, but now we don't have to say anything about nilpotence anymore, because in AN, the elements in AN are not only nilpotent, they are already 0 when taken to the power n. And the only thing that's left is to check that we can also put the axioms for the ideal in this other form. And nothing goes wrong. The most interesting thing is the 3rd line, x plus y is not necessarily 0 if taken to the power of n. If that's true for x and y, we have to take to the power of 2n minus 1. But that's not a problem. Okay, so these 2 theories here are Morita equivalent. And the right theory is a Horn theory. So we can at once conclude that the left theory is of pre-shift type 2. And that concludes the proof of the simplified case where we get here. And here is the general case. Maybe I should say 1 or 2 more sentences, because so in general the infinitesimal-topos is not just one topos that depend on 2 schemes, and it's not the entirely general case. This result, it's only for affine schemes spec R over spec K. And the theory gets a bit more complicated because we have 2 rings A and B then. One is a K algebra, but the other one is also an R algebra, and we need an axiom saying that F is surjective, which yeah, we can't make this Cartesian, so we need another strategy for the proof. And the strategy is, well, first leave out the difficult axioms here. So we start with an algebraic theory, just the theory of an A to B such that the square commutes. And then show that the induced topology of these additional axioms is a rigid topology, meaning that everything can be covered by irreducible objects, and irreducible are those that can't be covered non-trivially in any way. And when the topology is rigid, then by the comparison now we can show that the topos is a pre-shift topos. Okay, that's it, thank you.